Hello everyone, welcome you all at Lokesh Sir Unlimited Study Zones. So, in the chapter Semiconductor Electronics, we are here with the topic intrinsic semiconductor. Yesterday we have discussed that what is intrinsic semiconductor. Intrinsic semiconductor means pure semiconductor. Okay, a pure semiconductor which is free of every impurity is called intrinsic semiconductor. Examples are silicon and germanium. These are the example for say a pure semiconductor or intrinsic semiconductor. Okay, later on you know that silicon germanium is better than silicon because the energy gap requirement in germanium is only of 0.72 electron volt here. For germanium, there is an energy band gap equal to 0.72 electron volt, and for silicon, it is 1.1 electron volt. That is higher than the germanium. So, germanium is the better option. Fine. So, student, silicon, let us consider as a germanium crystal. For example, take a germanium crystal. So, germanium is an element of the 14th group, and the silicon and germanium both having how many electrons in their orbital? Outer orbital, there are 4 electrons. See here, this is the third orbit. The electronic configuration for silicon 3s2, 3p2. Likewise, here in the outer orbital, same 4 electrons are there in outer orbit. Clear? So, germanium having, check the electrons of germanium. This is first germanium's electron, second, third, and this is fourth one. Clear? These 4 electron are connected with neighboring 4 electron and make their octet complete. One, this 1, 2. Yes. Now see, in this way they have completed their 8 electrons. Clear? 1, 2, 3, 4, 5, 6, and 7, 8. Clear? And be bonded with the another germanium atom, covalent bond. Clear? Both the atoms, silicon and germanium, having 4 electrons, valence electrons. So the 4 valence electrons of a germanium atom form 4 covalent bond by sharing the electrons of the neighboring 4 germanium atoms. Or you can also take silicon structure. It's same like this. Okay. The 4 valence electrons of a germanium atom form 4 covalent bond by sharing of the electron of neighboring 4 germanium atom. The minimum energy required to break a covalent bond is 0.72 volt for germanium, and I said 1.1 electron volt for silicon. So this is the minimum energy to break a covalent bond. At room temperature, when an electron breaks away from a covalent bond, the empty place or vacancy left in the bond is called a hole. Okay, students. See here, I demonstrating here in what way the electrons are connected. Like silicon having its electronic number is 14. So electrons are like 2, 8, 4. So outer orbital orbit having 4 electrons. So 4 electrons are here as a valence electron. Okay. So check the silicon here. This is a silicon and it having 4 electrons are as a valence electron. These 4 electrons are working as a valence electron. They are well connected with a covalent bond with another silicon. Like this is one silicon, neighboring silicon, having its own 4 electrons. This is another silicon. This is 1, 2, 3, and 4. And this is one more silicon. 1, 2, 3, and 4. Likewise, the fourth one, silicon 1, upside and right, left 4. Getting my point exactly? So I'm talking about this silicon. So this silicon is bonded covalently by completing its octet, having 8 electrons. Fine. Now, at room temperature, when you given energy of like 1.1 electron volt for a silicon, suppose this electron get excited and leave its shell. Okay. And it comes till it is bonded, the time till the time it is bonded this electron is in valence band. Now, when you have supply some amount of energy and leave its place, then it uh, comes to the conduction band, okay, and getting out of the lattice. Yes. So 1.14 electron volt for silicon. At room temperature, when an electron breaks away from a covalent bond, the empty place or vacancy left in the bond is called a hole. Yes. Once this electron getting out from this place, a vacancy will be there. Okay, means a vacant place will be there. That vacant place is called a hole. Got it? Now, this is electron, this is negatively charged. So, if this charge is negative, then this empty place behave like a positive charge. Clear? So, electrons are negatively charged and holes are positively charged carriers. Clear? Electrons are negatively charged carrier. Now, what happening? Like this electron is attracted towards this place because they are oppositively charged. So this electron jump into this position and filled this position, and the hole will be created here. Okay, so this is the new site of hole. Clear? So simultaneously, the number of electron here equals to number of hole, because the number of holes exactly created in that number in which the electrons are created. Fine. Vacancy left in the bond is called a hole. When an external field is applied, these free electrons and holes move in the opposite direction and constitute a current. The number of free electrons and the holes are exactly equal in the intrinsic semiconductor. Yes. So we know the number of electrons equals to number of holes, but what is about applying of electric field? So like you have applied electric field, so this is plus and minus. Clear or not clear? Now you see this is electron. So electron will transit towards the positive charge. Clear? Electron is transit towards the positive charge. So electron transit towards the positively charge here. So outside current is from positive to negative, and hole will transit in this direction. Electron will transit from right to left, and holes will transit towards left to right. Understood? Because hole are positively charged carriers, so they're getting away from the positive plate, so they are traveling in this direction, and number of electrons equals to number of hole. Clear? So the total current I is given by total current in the circuit is given by I is equals to I electron plus I hole. Okay, so there will be two types of current. One is called electronic current and second is called hole current. So I E plus I H, electronic current plus hole current. Clear? Also, the conductivity of the intrinsic semiconductor is very low. Why? Because it is totally temperature dependent. Because the break of this bond totally depend on the temperature you providing here. Because on providing energy, this bond can only break. Okay. So the conductivity is very low. Yes, the conductivity of the intrinsic semiconductor is very low. The hole considered as an active participle in the valence bond having a positive charge equal to that of an electron. Yes, so you can understand this thing like this is the condition. Now there are two holes in the valence band, then there will be two electrons in the conduction band, because these are the number of electrons exactly equal to the number of holes. So holes will be in the valence band and electrons will be in the conduction band. Clear? Okay. So we have seen that the pure semiconductor is not good enough to provide you good conductivity. So we have to take another way to get a sufficient amount of electricity or conductivity. So this process is called doping. So what is doping? Doping is mixing. Okay. So you have to mix silicon, pure silicon or germanium. With pure silicon or germanium, you have to mix something. So what you have to mix? You have to dope these pure element with some another elements. This process is called doping. Doping is the process of addition of a desirable impurity. Yes, you have to mix impurity atom to a pure semiconductor to modify its properties in a controlled manner. Yes, modifies its property in a controlled manner. The impurity atom added are called dopants. Yes, the atoms you are doping are called dopants. Doping of a semiconductor increases its electrical conductivity to a great extent. Means now you are as a limited extent, and after doping you will get a great extent. Okay. So there are methods of doping, but that is not in our syllabus, so no need to read it. Okay. Now, after doping, you will have a new variety of semiconductor. Means when you have a pure silicon germanium, then after you have doped it with dopants, dopants, and you will have a semiconductor that is called extrinsic or impure semiconductor. Impure semiconductor. Got it? Extrinsic or impure semiconductor. So a doped semiconductor or a semiconductor with suitable impurity atom added to it is called extrinsic semiconductor. Extrinsic semiconductor are of two types. First N-type semiconductor and second P-type semiconductor. So extrinsic semiconductor are of two types. First is called N-type semiconductor and second is called P-type semiconductor. Why they are named so? N-type semiconductor and P-type semiconductor. Remember, N means negative. So when there is negative charge carrier is greater than positive charge carrier. Clear? Means electrons are greater than hole, then the type of semiconductor is called N-type semiconductor. And P-type semiconductor means holes will be greater than electron. Clear? Holes will be greater than electron. So there are two type of semiconductor, N-type and P-type. So first it is N-type semiconductor. Listen, in which way we can make the N-type semiconductor. So this is a pure semiconductor. You have to dope it. You have a two choices. Either you have to add as a trivalent impurity, 13th group impurity. 13th group impurity matlab 13th group impurity means boron, aluminium, gallium, indium. Okay, these are the 13th group with valency plus 3. And on the other hand, 15th doping with a 15th group elements, atoms. Means 15th group atom means nitrogen is a gas, so we can't use this, but you can use phosphorus, arsenic, antimony. Okay. So when you dope it with 13th group element, then a new semiconductor you found with the name as P-type semiconductor. And when you add the 15th group impurity, the semiconductor formed out is called N-type semiconductor. Clear? Okay. So when a pure semiconductor of a silicon or a germanium is doped with a pentavalent impurity, we are reading N-type first here. So when a pure semiconductor of silicon or germanium is doped with a pentavalent impurity, which having 5 valence electrons for phosphorus, arsenic, antimony or bismuth, then it is called N-type semiconductor. The 4 of the 5 valence electron of the impurity atom will form a covalent bond with the adjoining 4 atoms of the silicon, while the fifth electron is free to move. Thus, each impurity atom with added donates one free electron. Yes, first understand this. What is happening there? Like there is a impurity atom, you have added aluminium or boron. Okay, sorry, we are talking about N type, so we have to take the phosphorus or arsenic. So as it is the fifth group, 15th group means the outside in outer orbit there will be 5 electrons. So check here, this is the phosphorus. Let us suppose we have added phosphorus or arsenic. So there are 5 electron in lattice of 5 free electrons there. Okay. So silicons are there to make a bond with the phosphorus that is as impurity, silicon and silicon. You know the valency of silicon equals to 4. So yes, silicon 1 with a neighboring silicon 1, 2, 3, 4. So silicon has completed its octet. Clear? Here also this silicon contributed 1 electron. So 1, 2 and rest all a similar same. Okay, here 1, 2, 3, 4. So you see and here 1. So the 5 electrons of phosphorus 1, 2, 3 and 4. So out of 5, 4 are bonded, 4 are paired with the silicons, but still one electron is remaining here. Yes or no? That will behave as a free electron, and this electron is responsible for the electrical conductivity. Clear? So these four electrons are in lattice, so they are having some less energy. So these four electrons are the electrons of valence band. Clear, beta? But in conduction band, there is one electron. Clear? Conduction band, there is one electron. Initially, the energy of this valence electron is somewhat lesser than, it is only a bit of lesser than the conduction band, and this new energy level that is very close to the conduction band is called donor level. What it is called? Donor level, because this electron is behave as a donated electron, because it is just getting out of the lattice and will behave as a free electron. So just by taking very minimal energy, this electron jumps into the conduction band, and by the application of electric field it will constitute the current. So see, thus each impurity of atom added donates one free electron. Yes. What I want to understand, that each impurity, like one phosphorus, will give you one free electron. Clear? Yes. To the crystal, these impurity atoms are called donor atoms. These impurity atoms are called donor atoms. So phosphorus is called donor atoms. Donor atom. Clear? Okay. Since the conduction of electricity is due to the motion of electrons, that is negative charges, so that the resulting semiconductor is called n-type semiconductor, because of negative charges, electrons are there in the conduction band, so the semiconductor is called n-type semiconductor. Okay, see here, this is a typical example for n-type semiconductor. In that, arsenic atom is a donor atom. Here a free electron, arsenic provided this free electron. Now this is the valence band. Okay. Now this is conduction band, and just below the conduction band with a very minimum margin, it is 0.045 electron volt. Very less energy margin. There is a band of these free electron called donor energy state. Clear? Donor energy state. In n-type semiconductor, electrons are majority charge carriers and holes are minority charge carriers. Clear, beta? Yes. From where this hole can arises? Now see, if you have given some temperature, so by temperature excitation, like four electrons fetched out from their valence shell. So like this one getting out of this, and this one bond of silicon atom breaks here. Okay, one, two, one from here, three, and fourth from here. Yes or no? So now these four electrons jumped into the conduction band. One, two, three, four. One, two, three, and four. These four electrons jumped into the conduction band. Okay. And after four electron here in the conduction band, there will be a four hole also created in the valence band. So see here, four valence band holes, one, two, three, four, these are holes. Okay, and there is a four electrons, one, two, three, four electron is the conduction band, and here one is the donor level. So students, in n-type semiconductor, electrons are majority charge carriers and hole are the minority charge carriers. So these holes will be there, okay? Because of thermal agitation, hole will be there, and exactly the number of holes in valence band, there are same number of electron will be jumped from the valence band to the conduction band, but few electrons are from the donor level, so obviously number of total electrons obviously greater than the number of holes. So electron behave as a majority charge carriers. Clear? Yes. So this diagram is important. Donor level will be exist there. This is donor energy state having a gap of 0.045 electron volt. Clear? So you can understood it is better than the pure semiconductor, because in pure semiconductor there is a gap of 1.1 electron volt. That is very difficult to take this amount of energy. But 0.0545 electron volt is quite less. Done. Next, it's P type of semiconductor. So first, see what is the structure of P type of semiconductor. In silicon semiconductor, you have mixed with trivalent impurity like boron, aluminium, gallium. Okay. Suppose I have mixed boron. So atomic number of boron equal to 5 means 2 comma 3. Boron 5 electronic configuration equals to 2 comma 3 means outer shell valence shell having 3 electrons. Also it is from 13th group, so 3 electron will be there in the outer shell. So this is boron atom, and now this is first boron element, sorry, electron, second boron electron, and this is third boron electron. Clear? And this is the fourth one, bond like something, but there is no electron. Okay. So what happened? You see the silicon, so one silicon, this is second silicon, and this is third silicon with its own electron, silicon with silicon's electron, and the fourth silicon electron is here. Clear? So as there in this fourth bond of silicon, there is no any electrons. So this is behave as a vacancy and is called hole. Okay. So by one donor atom, there is one hole. There is one hole. Clear? So this is called P type of semiconductor. Now, when a pure semiconductor of silicon or germanium is doped with a controlled amount of trivalent atom. Trivalent atom means 13th group of atom. Clear? Which have three valence electron, boron, aluminium, gallium, indium, okay, in their valence orbit, then it is called a p-type semiconductor. Then it is called a p-type semiconductor. The three valence electron of the impurity atom will form a covalent bond with the adjoining three atom of the germanium. Yes, I said the three electrons from the boron, 1, 2, 3, they form a bond with the germanium or silicon, while there will be one incomplete covalent bond with a neighboring germanium atom. This deficiency of electron creates a hole. Creates a hole. So see here, this is indium. So three valence electron will contribute it to make a covalent bond with another three electrons. Yes, so there is a one bond here, one bond here, and one bond here. The fourth one bond is not completed, so there is a vacancy is called hole. Okay, the trivalent atom are called acceptor atom. So this atom indium is called acceptor atom. Clear? Trivalent atom is called acceptor atom, and this the conduction of electricity occurs due to the motion of holes. So how hole will transit? Like this electron, yes, occupy the place of hole, this one. So hole generated here. After then this electron came here, so hole will generated here. So in a way, this way, hole will move inside the lattice. Fine. So the resulting semiconductor is flowing current because of the motion of positive charge. That's why it is called p-type semiconductor or acceptor type semiconductor. Previously we have seen there is donor type of semiconductor, and here it is acceptor type semiconductor. Clear? Now you check about hole. So there is an acceptee, there is a level. See here, this is conduction band, okay, and this is valence band. This is valence band. ठीक है ना? So just above the valence band, just above the valence band, there is acceptor energy state. Acceptor energy state. This is a diagram for p-type semiconductor. Clear? P-type semiconductor. There is a acceptor energy state. Why? Because the transiting electron here uh, will occupy these holes having some energy greater than the valence band energy. So they will create their own level that is called acceptor energy state. Okay. So in p-type semiconductor, electrons are minority carriers and holes are majority charge carriers. So still you can feel here that n-type semiconductor is better because here the level of energy required to reach the electrons in valence band is quite less. But here still this amount of energy is needed by the electrons. Yes or no? So this much amount of energy is still needful. So this is not better. Okay. Now, a very important question was there in the examination. The distinction between or difference between the intrinsic and extrinsic semiconductor. Intrinsic means pure and extrinsic means impure. Collectively, it contains both P-type and N-type semiconductor. Clear? So, see, intrinsic semiconductor. It is pure semiconductor material and no impurity atoms are added to it. It is prepared by doping a small quantity of impurity atoms to pure semiconducting material. Example of crystalline form of pure silicon and germanium. Yes, pure silicon and germanium are the example of pure semiconductor or intrinsic semiconductor. Example here are silicon and germanium crystal with impurity of arsenic, antimony, phosphorus, etc. Indium, boron, aluminium. Yes. So p-type and n-type contains pentavalent and trivalent. The number of free electron always in conduction band equals to free electron equal to number of holes in the valence band. So number of free electron is the conduction band and the number of holes in the valence band exactly equal is, and still they are very small because they are thermally generated electrons and holes. Fine. The number of free electrons and holes are never equal. Yes. In a n types of semiconductor, number of electron is greater than number of holes, and in a p type semiconductor, number of hole is greater than number of electron. Clear? Yes. Yes. So number of holes greater than number of electron p type semiconductor. Its electrical conductivity is low, but here after doping you get semiconductor with a high electrical conductivity. So electrical conductivity of the extrinsic semiconductor will be high. Electrical conductivity is a function of temperature alone. Yes, I said that in the pure semiconductor, you can only depends on the temperature because temperature will responsible to break the bonds. So function of temperature alone. And here as well as temperature also doping intensity. Electrical conductivity depends on the temperature as well as the quantity of impurity atom you doped in the structure. Clear? I shown you in that diagram of n-type semiconductor. Like when you have given the temperature, so three bonds are breaking there. So three electrons are work as a valence, a conduction band electron. Okay. And in that three holes will be created in the valence band. Clear? And one electron is this free electron. Clear or not? Yes. So this is complete the difference between n-type intrinsic and extrinsic semiconductor. Next. Difference between n-type and p-type semiconductor. Okay. Okay. So n-type semiconductor and p-type semiconductor. N-type semiconductor is an extrinsic semiconductor which is obtained by doping the impurity atom with fifth group of periodic table of the pure germanium or silicon semiconductor. So you have seen with silicon you have to add with the pentavalent impurities. So will form a n-type. Here the extrinsic semiconductor which is obtained by doping of the impurities of atom of third group of periodic table from pure germanium silicon means in silicon you have to add the third group 13th group element. The impurity of yeah, impurity added provide extra electron, obviously. So here number of electron is greater than number of holes in the structure and are called donor atom. These atoms are called donor atom. The impurity added create vacancies of electron, that is holes in the structure, and are called acceptor atoms. Okay, so there is a donor level creation in the energy diagram. There is a donor level near the conduction band, and here the acceptor energy level near the valence band. The electron are majority charge carriers and holes are the minority. Here the holes are majority charge carriers and electrons are the minority. The electron density Ne is much greater than hole density. Yes, number of electron greater than number of holes. The hole density is much greater than the electron density. The donor energy level is close to the conduction band and far away from the valence band here. The acceptor energy level is close to the valence band. Here a new level is created, that is acceptor energy level, and that is far away from the conduction band. Fine, all the differences clear. Okay, so student, we have completed here the p-type semiconductor, n-type semiconductor, and now it's time to join both type of semiconductor, p-type and n-type. So in the left side we have a p-type semiconductor. Okay, in second side we have a n-type semiconductor. Clear? N-type here. So try to understand what is initial basics of p-type semiconductor. You know the p-type semiconductor, there are acceptor atoms, acceptor ions. Okay, here the donor atoms are there. So when any donor atom will be there, so it will donate your electron. So its charge will be positive because positive charge have a capability to donate the electron. Clear or no? So their core atom will be positively charged. So they are a core atom with positively charged with a free electron. And here core atom is negatively because they are acceptor atoms. These are called donor atoms. And p-type material contain acceptor atoms. So negative charge with a vacancy hole. Clear? So this is the basic structure for a n-type and p-type semiconductor. Okay. Hole, hole, minus hole, minus hole, minus hole, plus electron, 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 plus electron. It's like this. So a structure is like this. Now, when you join this, then it is called, then there is a formation of junction. This is called PN junction. And after joining the p-type semiconductor with the n-type semiconductor, collectively, this new device is called PN junction diode. Okay, because two terminals are here. So two terminals device is called diode. Diode means two terminals. Di matlab two, ode means terminal. So this is a two terminal device. Okay, and this is called PN junction. And this whole device is called PN junction diode or junction diode. Clear? Yes. So is we starting our next topic, PN junction diode. According to the syllabus, student, we have completed first energy band in the conductors, energy band in the semiconductor, and energy band in the insulator. Qualitative ideas we have completed. Extrinsic semiconductor and intrinsic semiconductor we have completed. Two types of semiconductor, P and N type. Now we are moving with PN junction. Okay. So first we see how a junction is formed there with the name PN junction. Okay. So PN junction. When a P type of semiconductor crystal is joined in N type semiconductor crystal, then resulting arrangement is called PN junction. Yes. So when you join a P type semiconductor with a N type semiconductor, this whole new arrangement is called a PN junction. Clear? Or it is called junction diode. Junction diode. Now, how you will form a PN junction? So different methods are there to forming a PN junction. To make a PN junction, the N-type and P-type silicon crystal are cut into the thin wafers. If on a wafer of N-type silicon, an aluminium film is placed and heated to a high temperature of 580 Kelvin, aluminium diffuses into silicon and a P-type semiconductor is formed, an N-type semiconductor. Such a formation is called formation of P region on N region is called PN junction. So this is the process of formation of PN junction that is not in our syllabus. So just ignore this. Now two things are there, student. One is called diffusion and second is called drift. Clear? Try to understand these two things. One is called diffusion and another one is drift. So when PN junction is formed due to the difference of concentration of charge carriers in two regions of PN junction, the electrons from the N region diffuses through the junction into the P region and holes from the P region diffuses into the N region. The motion of charge carrier gives rise to the diffusion current. Yes, see, there are two currents. First, it is diffusion current. Okay. So try to understand when diffusion current established. Like you just join the junction. This is the first time you have joined the junction. Just as you join this P layer with the N layer, now what is happening there? You can see that a P type of material is there. Okay. So P type of material, there is positive hole over negative immobile ions. So positive charges will be there. Fine. So there is a huge concentration of immobiles, huge concentration of holes. Sorry, here it will be positive donor atom with electrons. Clear? So here the concentration of electrons is very high, and here the concentration of holes will be very high. So what will happen? Due to the difference of concentration, they will move towards each other. Yes. So electron is moving towards hole, and hole will be moved towards electron. Clear or not clear? Electron will move towards hole, and hole will move towards electrons. Clear? Means charge carrier from the p junction will move towards n type, and charge carriers from the n type will move towards p type. Fine. Okay. So you know there is a flow of current. So this hole will constitute a hole current IH. So when positive charge is moving, so the current direction of current is along with the direction of particle, charge particle. So there is a hole current. Clear? And electron is moving in the opposite direction of motion of electron. There will be a current that is called electronic current. So total current I equals to I hole plus I electron. So total current I equals to I hole plus I electron. Clear or not? Yes. So this current is called diffusion current. First, it is this current be established because of the concentration difference is called diffusion current. Clear, students? Once again, when a PN junction is formed due to the difference in concentration, underline difference in concentration of charge carriers into the two region of PN junction, the electron from N region The electron from N region will diffuse through the junction into the P region, and the holes from the P region, okay, will diffuse into the N region. The motion of charge carrier give rise to the diffusion current across the junction. Clear? Yes. So this is happening here. This is P region. This is N region. Okay. Now you see after some time, after some time when now this is P part and this is N part. Now, P part having negative immobile ions with holes. So only negative immobile ion will left because all the holes near to the junction are just recombined. Because when a hole and when an electron is met together, then holes is a positive charge and electron is a negative charge. So this is called recombination. Clear? This is called recombination. So they will cancel each other. So only negative immobile charges will be left near the junction this side, and only positive charges will be left here near the junction. So positive and negative immobile charges will be there. Okay, these are core central ions. Core ions. Clear, beta? Okay. So see here after recombination, yes, negative charges are here, and positive immobile charges. Yes, uh, the this one these are free electrons and free holes are said to be mobile. Yes, so these are what? These are mobile charges. They are allowed to move, mobile charges. But this positive and negative sticked in the lattice, so they are called immobile charges. Fine? Yes, immobile charges. So these immobile charges created a layer. Okay, there is no any free charges found, and this layer is free from the free charges. Free from the free charges. So this layer is called depletion layer. Clear? This layer is called depletion layer. You see the electrons from the N region get transited and enters into the P region. Yes, this is the electron entered here from the N region. Okay, and some holes here, those are entered from the N region, P region, and here comes into the N region. Clear? Yes, so these are the holes in the N region. These are the electrons in the P region. Electrons and holes are in opposite region, and this layer is called depletion layer. Clear? The negative immobile ions, the negative immobile ions will produce a very less negative potential. Collectively, they will produce a less negative potential as the negative charge accumulated here near the junction. So they will form a very less negative potential. And after the accumulation of positive charge, there is a creation of very less amount of positive potential. So this is called a small potential difference is there. This is called barrier voltage. Fine. This is called barrier voltage. Huh. So the due to the diffusion of electrons and holes, a layer of positively charged donor atom in the n region and a layer of negatively charged acceptor atoms. Acceptor means negative. Negatively charged atoms in the p region are created. Yes. So this positive and negative space charge region on the both side of the pn junction will form a region which has immobile ion only, and it is called depletion. Depletion means vacant or empty. Empty from what? Empty from mobile charges. There is only the immobile charges. See here, no mobile charges are there. Only they are immobile. There is no hole, there is no electron. Only these core atom ions are present. So this layer is called depletion layer. Fine. The layer is free from electron and hole. That's why the name of this layer is called depletion layer. Clear? Huh. So due to the positive and negative space charge region at PN junction, a electric field is set up across the junction. Yes. Due to this electric field developed at the junction, an electron on the p side of the junction moves to the n side, and holes on the n side of junction moves to the p side of junction. This motion of these charges carriers due to electric field is called a drift. As a result of it, a drift current starts, which is opposes in the direction of diffusion current. Yes. See here, student, what happening here. Previously, you have seen there is a diffusion current because electron is diffusing into the p region, and holes are diffusing into the n region. Clear? We have seen the diffusion current. Yes, we have seen here. This is diffusion current from hole, and this is diffusion current in the same side from electron. Now, what is happening there? There is a creation of drift current. Why? The drift word is only developed, only present there whenever there is a electric field. So you see there is a positive and negative. So electric field will be there. Clear? Now what happening here? These holes, now these electrons, previously, you know, the electrons are moving towards here, but now the electrons which are in p region, yes, I'm talking about these electrons. Now the electrons are in p region will rush towards this junction, and holes also in n region will rush towards this junction. Why? Because there is a electric field. Clear? Because negative potential attract these holes, and positive potential will attract these electrons. Okay. So see, there is a opposite type of current will be yes. That time during diffusion current, there is a current developed outside, like this is outside. Okay, but now there is a creation of hole current this side, also electron current this side, because electrons are moving towards here. Clear? So opposite direction current will be developed here. So see, yes. Due to positive and negative space charge region at PN junction, electric field is set up across the junction. Due to this electric field developed at the junction, an electron on p side, yes, electron on p side of the junction moves towards the n side, and the holes on the n side of junction means these are minority charge carriers. move toward the p side of the junction. The motion of these charge carriers due to the electric field is called a drift. Yes, whenever there is electric field, this motion is called drift. As a result of it, a current is start, which is in opposite direction of the diffusion current. Yes, clear? Huh. In the beginning of the diffusion, in the beginning, the diffusion current is large, but drift current is small. As the diffusion process continues, the strength of electric field across the junction increases. Yes, when you just mix the junction, mix this layer, it start particle will diffuse in very high speed. So that time diffusion current will be more. But as there is a creation of these immobile charge layer and electric field is established, what happening? Drift current increases in opposite direction. Means first diffusion current increases. Okay, now it is drift current increases. So one side there is a increase of diffusion current, but now there is slowly there is an increase of drift current. Okay, both in opposite direction. Okay, electric field across the junction increases and thereby drift current also increases. This process continues until diffusion current becomes equal to the drift current. So at any time, there is a drift and diffusion current, both are equal. Clear? Equal to the drift current. Now the PN junction is said to be in equilibrium state and there is no current across the PN junction because drift and diffusion current both cancel each other as they are flowing in opposite direction and there will be no current. Okay. In this state, PN junction is called in equilibrium. Clear? There will be no current across the PN junction. At this stage, the potential barrier across the junction having the maximum level. Yes, maximum value. So this time, the junction, the potential barrier having the maximum value VB. Now there is now the moment of my majority charge carriers, the junction stops and the potential act as a barrier. Hence, this is known as the barrier potential. Clear? So this potential of this side here it is negative and here it is positive. This potential barrier is called barrier potential. Got it? Yes. Check here. This potential barrier is called barrier potential, which prohibit the further movement of charge particles. At a room temperature 300 Kelvin, VB is about 0.3 volt for silicon, sorry, for germanium, and 0.7 volt for silicon. So remember the value of VB for germanium, it is 0.7 volt, okay, at a room temperature, and for silicon, VB equals to 1.1 volt. The value of VB increases with rise in temperature for germanium and silicon. The value of potential barrier increases with rise in temperature. Now, so this is complete about the formation of PN junction, okay, and formation of depletion layer. So student, till now we have completed the PN junction diode and formation of the depletion layer. We have seen the two types of current, diffusion current and diffusion current and drift current. Okay, and seen after some time uh, the diode will not permit to flow of any current through it. Okay, so now we are going for the biasing of semiconductor diode or PN junction diode. We are giving the supply to this semiconductor and giving supply of this semiconductor is called a biasing. So what we going to do, like this is a PN junction, this is P and this is N. Now P and N. Okay. Symbolically, the PN junction is denoted by this P and this layer is N because it is not and quite understandable. So this angle is looking good also. This layer is called P and this is called N type material and this junction is called PN junction and this device is called diode. Clear? So we are energizing. We are going to energize this PN junction diode. Okay, so there are two type of energizing method and that is called biasing. Biasing. First, we can connect the P terminal with the positive terminal of the battery and N terminal with the negative terminal of the battery. So this type of biasing is called forward bias. This is called forward biasing. Clear? Second, it may be we can connect P terminal with the negative supply and N terminal with the positive supply. This biasing is called reverse biasing. Okay? So two type biasings are there, forward biasing and reverse biasing. So biasing of the PN junction, there are two method of biasing of the PN junction, forward biasing and reverse biasing. So we are moving with biasing of PN junction. So there are two methods of biasing the PN junction. One is called forward biasing. Second is called reverse biasing. So first see forward biasing. Forward biasing means when a PN junction you connected the P type of semiconductor with the positive terminal of the battery and N type of semiconductor with the negative polarity of the battery, then this junction, PN junction or PN junction diode or junction diode is said to be in forward biased. So PN junction is said to be in forward bias if the positive terminal of the external battery is connected to the P side and the negative terminal of the battery is connected to the N side of the PN junction. Fine. Now see what is happening when you connected the P junction, P material with the P side, positive side, and N type semiconductor with the negative. So you know there is a barrier potential that that time diffusion current equals to the drift current and the current from the junction becomes zero. Clear? Yeah. Okay. So when you applied here the battery, the positive terminal towards the P type of material, these holes get energized or get repelled by this positive because this is positive terminal. So holes are also positive charge carriers, so they get repelled and they rush towards the junction. On the other side, the electron from the N type of semiconductor also get repelled here and they rush towards the junction. Bolo yes or no? Okay. So on forward biasing, yes, this is a symbolical diagram. See here, this is P type of junction, P type material, this is N. P connected with the plus and N connected with the minus. In forward biasing, the forward voltage opposes the potential barrier. Now see here, you have applied your voltage plus and minus this side. So there is a creation of outer voltage this side. Okay, from left to right. Electric field, you know, is moving from left to right. Clear or not? And here the barrier voltage, electric field from the barrier voltage is from right to left. So this is the barrier voltage. Clear or no? This is E barrier. Let us suppose you have applied here voltage from 0 volt and trigger it. Okay, so there is a some triggering like devices there. So you can increase from 0, then 0.1, then 1, 2, 3, 4 like this. Okay. So what is happening there? First, there is existence of the this barrier voltage when their junction is formed. But as you applied here the biasing voltage, first it is very small. Okay, and this barrier voltage is equals to for silicon. This is equals to 1.1 volt. Clear or not? It is of 1.1 volt for silicon. We just read that it is 1.1 volt for and silicon. Sorry, for germanium it is 0.3 volt, and for silicon it is 0.7 volt, not 1.1. 1.1 electron volt is a barrier energy gap. So this is 0.1 volt voltage here from the this battery VB. Now you have applied a voltage of 0.1 volt. Okay, then only minute electric field will there. But as you increase your voltage, a time came when you have exactly applied 0.7 volt battery here. Then what will happen? These both potentials get cancelled. These electric field get cancelled each other, and there is a open path for both the carriers. Clear? Because this outside electric field we have applied is cancelled the inside electric field. Clear? Yes, this eradicate all the VB barrier potential, okay, and and your external electric field having impact, so the holes will move towards the N region, and the electrons will move towards the P region. Yes, see here. Okay, in forward biasing, the forward voltage opposes the potential barrier VB. You know, the potential barrier VB is in opposite direction, positive here and negative here. So this is your potential barrier VB battery, and your outer voltage you have applied is positive this side and negative this side. Clear or not clear? So your external voltage will be in opposite direction. So the time your external voltage crosses the barrier voltage or crosses the barriers, as a result of it, potential barrier and width of depletion layer decreases. So the depletion layer will be decreases, and effective value of the for potential barrier in forward biasing equals to VB minus V. VB minus V. It is also said as V minus VB. Why? Like you have applied a voltage of here 1 volt. Okay. So you have applied a voltage of 1 volt, means plus and minus 1 volt of potential is applied here, and here it is equals to how much? 0.7 volt. So the effective voltage equals to 1 minus 0.7. This is equals to 0.3 volt. Clear or not? Okay. So this is the forward biasing voltage. In this way, what happened here? Check by the characteristics diagram. Yes. So initially, till you are at 0.7 voltage, there is no flow of current. Okay. Because your barrier voltage stops the movement of the charges here, because there is a voltage of 0.7 is barrier. Clear? So till you have applied your external voltage less than 0.7 voltage, there is no movement of current. But as you applied exactly equal voltage, so electric field in opposite direction will cancel the barrier electric field, and this gate that was closed for the holes electrons, now this gate collapsed. Okay, this layer collapsed, and there is a free entry for holes and electron, and correct current will increase very high. Clear or not clear? So there is a flawless increase of current, and this is called conduction, and this is called very low resistance because current increases very high. So this will offer a low resistance path. Clear or not clear? So there is a low resistance path, and this is called forward current. This current is called forward current, and this characteristics is called forward characteristics. Clear? Now, talking about the next type of biasing, this is that is called reverse biasing. So in the forward biasing, we have seen that you connect the positive terminal of the battery with the P plate and negative terminal of the battery with the N plate. Okay. But now just make the opposite connections. Connect P with the minus and connect N negative junction diode with the plus. Okay. Make it just opposite. Then this biasing is called reverse biasing. And PN junction is said to be reverse bias if the positive terminal of the external battery is connected to the N side and the negative terminal of the P side, negative terminal to the P side of the PN junction. Yes. In reverse biasing, the reverse bias voltage support the potential barrier VB. Now what is happening there? See here what is going to happen. This is a P-type material and this is N-type material. Now there are holes. Here the immobile positive charge ions with electrons. Few electrons are here. Okay, and here the negative immobile charge ions, and here negative with holes. Clear? So students, here when you apply the reverse biasing, this is P type of material and N type material, and you connected here the P type material with the negative battery. This is depletion layer. Okay, and N type with a positive battery. So what will happen? These electrons now get attracted towards this plus polarity and get entered into the positive terminal side, and holes from this region, okay, enter to this negative region. Clear or not clear? As a the result of this, this total place becomes vacant from the region, vacant from the whole cell electrons, and depletion layer increases because negative, negative, negative and mobile ions will be only there as the charges, mobile charges are accepted by the respective poles, respective terminals. Clear? So depletion layer will be increases. Now the depletion layer, previously in the forward bias, depletion layer was reduced, but here the depletion layer increases. So the NPN junction in reverse biasing, the reverse bias voltage support the potential barrier VB. As a result of it, barrier potential and width of the depletion layer increases. Yes, barrier potential always as well as width of the depletion region increases. Yes, so depletion region increases here. The effective value of the barrier potential voltage under reverse bias equals to VB plus V. Why? Because your previously your electric field is working here from plus to minus. So plus to minus your electric field is here. But now your applied electric field, this is plus to minus. So this become plus and this become minus. Means in the same direction, your external electric field is working. Clear or not clear? So your effective voltage will be increases VB plus V. Clear? So in this way, you have your reason. Now what is happening here? All the holes will rush towards this negative terminal and all the electron will towards move towards the positive terminal. Clear or not clear? Yes, electrons move towards the here and holes move toward here. Clear? Only a few minority charge carriers like the electrons, drifted electron present in the p type. So electron will move towards this side and the drifted holes, those who are present in the n side, will move towards the negative terminal. So only a very few ampere, very less ampere will created during the reverse bias. This current that is very less in amount is called reverse saturation current. Yes. Yes, remember the current? This is called reverse saturation current. Clear? Yes, this current flows because of minority charge carriers in the different side. So this is the diagram. P layer and N layer. P is connected with the negative terminal and N is connected to the positive terminal. Clear? Now, on reverse biasing, there is no conduction across the junction due to the due to the majority charge carriers. However, a few minority carriers of PN junction diode cross the junction after being accelerated by high reverse bias voltage. They constitute a current that is called reverse current or leakage current. Yes. So these minority charge carrier that crosses the junction will form a very less amount of current and that current is called leakage current. Clear? Okay. So this is called leakage current. Okay, next is characteristics of PN junction diode. Characteristics means the curve between voltage, applied voltage and current obtained. Okay. Voltage you will give as an input and current will result as output. So you have to make the necessary circuit. So first we are taking the characteristics diagram for forward biasing. So here this is a diode. Okay, so to find the voltage, just make a voltmeter that connect in parallel. So this is a voltmeter and this is a battery. From a battery, you have to take a rheostat. So to change the applied voltage, to trigger the voltage, okay, 0, 1, 0 volt, 2 volt, 3 volt, 4 volt, likewise. And from this terminal, so this behave as a negative and this behave as a positive. You just take in this amount of voltage that will passing through a milliampere in a series circuit. So this is the completion of circuit now. On plotting graph between the forward bias voltage, first it is forward bias voltage and forward current, we get the following graph. So I'm talked about this graph first till the threshold voltage. It is also called knee voltage when you have applied lower than 0.7 volt for silicon, like you have applied a 0.6 volt. So no current will be flown there because there is a barrier voltage of 0.7 volt. Now, as you applied 0.7 volt, so this applied electric voltage cancelled the barrier voltage and charge carriers are free to move across the junction and current will raise highly. Okay, so it is found that beyond forward voltage, this is V equals to Vk. It is called knee voltage or threshold voltage. This is 0.3 volt for germanium and 0.7 volt for silicon. The current through a junction start increasing rapidly with voltage and showing the linear variation, but below knee voltage, the variation in current is negligible and the curve is as non-linear. So here the current very less, but after this current increases very high. Okay, the current through the junction start increases rapidly with voltage showing a linear variation. So after conduction, your current is in linear variation, but below the knee voltage there is the variation in current is negligible and curve is non-linear. So all total this curve is equals to non-linear, means this is called non-ohmic. Non-ohmic. Because the conductors are ohmic conductors, metals are ohmic conductor, they following the V proportional to I characteristics, but here you cannot say that V is proportional to I. Clear? So this is called non-ohmic conductor, so it not followed the Ohm's law. Reverse characteristics, yes. First we have seen the forward characteristics. Now second it is reverse characteristics, means reverse bias characteristics. So in reverse bias characteristic, just opposite the battery, means take this one negative and take this one positive. Rest all the diagram is fine. And here is a voltage. And now previously during the forward bias, you have to take the milliampere because the current is in milliampere range. So here the current will be measured in milliampere. But in reverse bias, the current will be in microampere. So here the current is in microampere. Check. On plotting a graph between reverse bias voltage and reverse current, we get a reverse characteristic as shown in figure. So I said you by increasing the voltage due to the applied increase voltage depletion layer increases, but the minority charge carriers like electron in the p region and holes in the n region will transit about the junction and will constitute a very small amount of current. That current is called reverse saturation current, or it is called, yes, reverse current or leakage current. Okay, so this amount of current here is flowing. Yes, you can check, this is the amount of current. This is called leakage current. Clear? Leakage current. You see, during the forward bias, just after apply a voltage of 0.8 volt, suddenly there is high region of current is flowing. But here in this situation, reverse bias, you have applied minus 2 volt, minus 4 volt, minus 6 volt, minus 8 volt. So there is very less amount of current, only a few microampere. But as you apply more than minus 8 volt, then what will happen? These lattice bonds like silicon, which is connected with another silicon with their valence electron. Now these valence electron, there is a breakdown takes place because of very high electric field. Okay, very high electric field. There is a breakdown in the lattice and electron will moves towards the positive direction. So suddenly there is an avalanche, there is a breakdown taking place and a current becomes very high, very high. Okay, and because of very high current, the temperature of the junction increases very much. This is called breakdown voltage. So at this point, the breakdown takes place. This voltage is called breakdown voltage. Okay. On plotting a graph between reverse bias voltage and reverse current, we get the reverse characteristics as shown in figure from the curve, we note that in a reverse biasing of PN junction, the current is very small, yes, in microampere and independent on the voltage up to certain reverse bias voltage called breakdown voltage. Means it, I mean to say there is a very less amount of current is flowing during the leakage current as a leakage current before the breakdown. Okay. However, you try to increase the voltage, but there is no impact. Only a less amount, like you came from 0 to 0.1, 0.2, 0.3, 0.4, 0.5, 1.1, 1.2, but only a small amount of current is flowing because due to of minority charge carriers, okay, a very less amount of current is flowing. But if the reverse by if the reverse bias voltage exceed the breakdown voltage here, after breakdown voltage, the reverse current through the PN junction will increase abruptly, suddenly. If the current exceed to the rated value of the PN junction is specified by the manufacturer, the PN junction will get damaged. Okay. So current increases here and the PN junction may be damaged. So this is called characteristics of the PN junction diode in reverse biasing. So here you have two type of characteristics. One is called forward bias and second is called reverse bias. That is very, very important. So this topic we have cleared as name of IV characteristics, current voltage characteristics in forward bias and reverse bias. Our next topic, students, application of junction diode. So use of diodes as a rectifier. So let us perform the application of junction diode. So student, you seen the things that in forward bias, during the forward bias, diode conduct heavily. You seen? The diode conduct heavily in a forward bias. Yes. And but in reverse bias, diode, so means in forward bias, diode conduct heavily means it offers a low resistance. Clear? Yes or no? It offers a very low resistance during forward bias, but in reverse bias, it offers very high resistance. You see, up to here, okay, do not come to the limit of breakdown. So here, the very less amount of current means almost diode not conducting, or you can say very high resistance, very high resistance. Clear? So two reasons are there. First is very less resistance and second is very high resistance. Okay. So two reasons are there. So use of by taking the advantage of these two conditions, we are going to use the use of PN junction diode as a rectifier. So PN junction diode as a rectifier. Rectifier, what is rectifier? So rectifier is a device which is used for converting alternating voltage or current into a direct current or voltage. So you have alternate voltage or current supply, okay, and you are going to use, you want direct current, so you have to use a rectifier. So what is rectifier? Let us see what is the aim of rectifier. Like you have a AC current like this, and you want a proper DC current to use your charger to recharge your mobile. So what- you have a adapter that takes AC from your domestic AC socket, okay, and convert it into the DC. So you taking the AC at 220 volt and you convert the DC supply. So as an input, you take the AC supply with a 50 hertz frequency and you convert into a DC supply of a frequency of 0 hertz, okay, and 3 volt. So how can you obtain this? So the major part, the very important, the very first part you use here, the important part is a rectifier. Okay. So rectifier is used to convert your AC supply into the DC supply. Clear? So there are two type of rectifier. First, so definition, rectifier is a device which is used for converting alternating current or voltage into direct current or voltage. There are two type of rectifier. First is half wave rectifier and second is full wave rectifier. Okay. So what is half wave rectifier? So half wave rectifier, introduction of half wave rectifier means you first see this is your input signal voltage. Okay. So half wave rectifier will crop the negative signal and only produce positive signal, output signal as a output. Okay. So this is half wave rectifier. Only positive cycle supply will be provided by the diode and negative cycle supplied it will be emitted or okay blank, no signal will be presented there for a negative cycle. Clear? So this is called half wave rectifier. See how it's work. AC voltage to be rectified is connected to the primary winding of the P1, P2 of the step down transformer. So you have a AC supply of 220 voltage there. As you need a output of less supply, 3 volt. So you have a step down transformer. So first this step down transformer primary winding N1 is high, N2 is less. So step down the voltage. Suppose there is a conversion of output voltage in plus minus 3 volt. So there is a AC supply of 3 volt. Now it is converted into 3 volt AC. Okay. Step down transformer. S1, S2 is the secondary coil of the transformer. S1 is connected to the portion P of the PN junction. Yes, see here. S1 here is connected to the, this is positive terminal, and S2, this is negative. S2 is connected to the negative terminal of the battery through a rheostat. Okay, you're taking here output voltage here. Hmm. S1 is connected to the portion P of the PN junction. S2 is connected to the portion N through a load resistance R. Output is taken across the load resistance R. So working is there like during the first half cycle, when during the positive half cycle, what will happen? The supply will be like this. This is plus and this is minus. Okay. So if this is plus and this is minus, the resultant polarity will be here plus and minus, means your diode getting in forward bias during the first half cycle. So during the positive half cycle of AC, suppose S1 become positive and S2 become negative, then the PN junction become forward bias. So this S1 terminal become positive and this terminal become negative. So your PN junction become forward bias. So the during the PN junction, you know the registration, the resistance become less, and this diode comes into the conductive mode. PN junction in forward bias, the resistance of the PN junction becomes very low, and the maximum forward current flows in the circuit. We get output across the load. So this diode will conduct the current, and after passing this current in this direction, like there is resistance R, and if this current is going through this resistance, you will having some voltage. Yes, so exactly same amount of voltage will be drawn here or across the load resistance. Now next half cycle, during the negative half cycle of the AC supply, now this terminal becomes negative and this terminal becomes positive. Yeah. During the negative half cycle it's AC, S1 becomes negative and S2 becomes positive. The PN junction is now reverse bias. It offers a high resistance and hence there is a no flow of current and thus no output across the load. Yes, you know, if this becomes negative during the half cycle, negative half cycle, this terminal become negative, and due to this plus, this terminal become positive. So this diode came in reverse bias. Clear? And during the reverse bias, you know there is no current, so a blank space for next half cycle will be there. No current will be there means I equal to 0. So positive cycle is conducted as it is and no negative cycle. Again, when cycle changes, positive cycle for positive input cycle, there is a conduction. Okay, so this process so many times happened again and again. Hence, in the output, we have current corresponding to the one half cycle of the wave, and the other half cycle is missing. Clear? That is why this process is called half wave rectification, and this type of rectifier is called half wave rectifier. Clear? Next is full wave rectifier. So, full wave rectifier is used to complete produce a full wave. So there are two diodes are used. So check here. Actually, previously we have seen in the during the half wave rectifier, the diode only conduct the half of the wave. Okay, so that's why you having the half of the wave only as a output. But now you will have a both the cycles from the full wave rectifier. So, what you have to do full wave rectifier for full wave rectifier, we have to use two PN junction diodes. So previously you have used D1, but here you have to do use D1 and D2, and with a special type of transformer. This is called central tapping transformer. This is called central tapping transformer. So this circuit is given below here. So check here. This is your primary winding. This is your secondary winding, and next one diode is on this side and another diode on the this side, and from a central point of the transformer you have to take a output load resistance as a to take as the output. Now what is happening there? First, in the first supply positive half cycle, when during a positive half cycle, this terminal become plus and this terminal become minus. So due to the induction, this become plus and this become minus. You know, if this is plus, this is minus, then there will be zero potential at the mid of the coil. Clear? So now this polarity become positive, and so high potential, and this become in low potential. So no potential is assumed or considered as a negative. So this diode is they will conduct, okay, and flow the current. But at that time, this P terminal is negative and this terminal, the N terminal is zero. So when P terminal is negative, so this diode comes under reverse bias. So only one diode will work under the forward bias. So you will have, after the action of D1 diode, you will have an output from the D1 diode here. Clear? D2 is inactive. Now when this cycle changes after half cycle, this polarity becomes positive and this become negative. Clear? Because after the half cycle, the direction of current changes. So from positive to negative, the correct current will reverse. So if this become positive, now this diode comes in the forward bias, and after getting this one negative, this diode comes in the reverse bias. So again, the direction of flow of current is from here to here. From upside there is no current because this one now is in reverse bias, so no current will be there. So the total current will enter through the same direction and will drop again voltage in the same direction. So you will have, by the application of diode D2, again you have the voltage. Then again D1 comes to the forward bias, and then again D2 comes to the reverse bias, and they conduct and so on. Fine. Mhm. So this is the diagram. So during the positive half cycle, yes, this is the diagram for positive half cycle only, and this is for negative half cycle only. See, this diode comes in the forward bias and this comes in the reverse bias. So there is no conduction from this, but there is conduction from this. So current is drawn from the load in the same direction and will produce the output plus and minus across the terminals. Clear? The circuit is shown in figure given. Working during the positive half cycle of AC, the diode D1 is in forward biased and the diode D2 is in reverse biased. The forward current flows through diode D1 in the direction as shown in figure. During the negative half cycle of AC, okay, you have seen in the first half cycle, diode D1 is working and current. Okay. During the negative half cycle of AC, the diode D1 becomes in reverse biased and the diode D2 in forward biased. So the forward current flows through only diode D2. We observe that during the both the half cycles, AC current through the R flows in the same direction. Means in first cycle, the current is flown from the load from left, right to left, means plus here and minus here. In the second half cycle, when D2 is working, current is flowing through the same direction, means same positive and same negative will be there. So same in the same direction, current will flow. So you have the voltage in the same polarity. So D1 and D2, you have the voltage from the same polarity. Hence, the output signal voltage is unidirectional, means your voltage will have the polarity again plus to minus in the same direction, having ripple contents, that is DC component and AC component of voltage. Means this voltage is not perfect DC, this is pulsating DC, means also it having sudden jerks are there again and again. So this is called pulsating DC. It having the some AC component, it can be converted into the pure DC voltage by filtering through a filter circuit. So after then you will require a filter circuit. Then by using a filter circuit, you will be have a voltage like this, like input voltage is there, uh, like this. But you use rectifier, you got, after rectifier you have a pulsating DC. But after then you will use a filter. So by the use of filter, you have a current like this. Okay. Then finally, you have to use a stabilizer. This will stabilize your voltage, and you have a final DC voltage of 3 volt. Now you can plug in your charger and can recharge your mobile. So this is your full wave rectifier. Clear?